Yes, it's Uncle Jegs. Today's video is all about the specific heat capacity required practical. First, I'll touch on the theory of specific heat capacity, then I'll look at the required practical itself. Then after the required practical, we'll look at how to analyze your results and also the type of graph that you need to draw. As always, check out the worksheets in the description. Use the time skips to skip to exactly what you need. And yes, without further ado, let's get that peng. On a very hot day, you may notice that the metal surface of a car feels a lot hotter than the walls of your house or even the concrete on the road. The house, car and roads are all absorbing the same amount of heat energy, but for some reason they do not increase in temperature by the same amount. The metal of the car seems to increase in temperature easier, while the concrete needs a bit more energy to increase to the same temperature. This is our first clue in understanding this practical and its equation. The energy needed depends on the type of material we're using. Now, what would you expect if we have two pieces of metal? One is 1 kilogram and another is 5 kilograms. I applied the same amount of heat to them. Which one do you expect to have the higher temperature? If you said the one that was 1 kilogram, then you're absolutely right. That's because it has less particles inside it than the 5 kilogram material. They both receive the same amount of heat energy, but this heat energy needs to be evenly distributed amongst the whole material. That means that in this example, the one that's 1 kilogram receives all of that energy, while there's 5 particles in the 5 kilogram one receive that energy evenly distributed. Temperature is the average kinetic energy of the particles in a substance. This means that the 1 kilogram metal will feel hotter. This is another clue to our equation. The mass of the material, the amount of particle it has, is important to understanding the energy transferred. The last part of the equation is a pretty obvious one. From the previous examples, we know that the energy we need depends on the mass and the type of material that we're using. But look here, I have two materials that are both identical in mass and substance. But I want to increase the one on the left to 5 degrees Celsius and the one on the right to 10 degrees Celsius. Obviously, I need to put in more energy to the one on the right, and that is the last part of our equation. The equation is complete. The energy we need to put into something depends on the mass, the type of material, and the temperature change. Let's look at how this works in using the scientific keywords. The energy should be energy transferred, and this should be in joules. Mass is okay as mass, and that should be in kilograms. The type of material should actually be called the specific heat capacity, and the units for this one's a bit of a mad one. It's joules per kilogram degree Celsius, and obviously temperature change should be in degrees Celsius. Specific heat capacity is the energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. One thing you're expected to do in your practical is calculate the specific heat capacity of your material. Looking at our equation, that means that we need to get the specific heat capacity by itself. In order to do that, we need to get rid of the mass and the temperature change on the right hand side. We do that by dividing both sides by the mass and the temperature change, so that on the right hand side, the mass and temperature change cancel each other out. But wait, as I said, we need to do it on both sides. So the left side is equal to the right side, which means that the final equation for specific heat capacity is your energy transferred divided by your mass times your temperature change. Mass is obviously measured using our scale. Temperature change, we're going to need our thermometer to measure the initial temperature and then the final temperature, and then we'll work out the difference between the two. And then finally, energy transferred is measured using something called a joule meter, which bizarrely measures the joules of energy transferred. Okay, time for the practical. So we start off by measuring the mass of your metal block in kilograms using a scale. Then you wrap this block around with insulation, because obviously we're trying to limit the amount of heat that's escaping to the surroundings. You then place the heater inside one of the two holes that you have in the block. This is going to be the bigger hole. This is when you connect an ammeter and a power pack in series to that heater, okay? And your voltmeter then is connected parallel to your heater. You use a pipette to drop a small amount of water in the smaller hole, which is where your thermometer is going to be placed. With the power pack on 12 volts, switch on your power pack and record the amps and potential difference in a table like this one here. You then measure the temperature and start the stop clock. Record the temperature for every minute for 10 minutes in a results table like this one over here. You repeat this for the different blocks that you have. Usually you'll probably be given 3 or 4 blocks to use. Now it's time for some work with those physics equations because we're going to be analyzing our results. The first one is the equation for power. This is simply your current times your potential difference. Then you have to work out the work done, which is simply your power that you just calculated from that last equation, and you multiply that by the time. And notice from your results table, you have to keep increasing because you're timesing it by the time that you have. You will then finally need to draw a graph with your temperature on your y-axis and your work done on your x-axis. When you work out your gradient, and check out my video on how to think like a scientist to see how we actually draw gradients, you will need to use that to work out your heat capacity. And your heat capacity in this context is 1 divided by your gradient. And after that, you then work out the specific heat capacity of your material. So, specific heat capacity, remember, is your energy transfer divided by mass times temperature change. The energy transferred here is just going to be the work done, what you get from your x-axis, the change from your x-axis. Your mass is obviously the mass of your metal that you worked out by putting it on a scale. And then finally, the temperature change is essentially the change in temperature that you measured. You repeat this, as I said, with the other blocks, and then check with your teacher to see if your values are roughly the same as the true values. And that, ladies and gentlemen, is it for this video. Check out the work in the description, and if you're still baffed, use the timestamps to skip to what you need to. Like, comment, bell and all that jazz, and don't forget that science is more than just a body of knowledge. More importantly, it's a way of thinking. Think big, innovate.